made of atoms. And the atoms are made of what? The atoms have a central nucleus, say positive, and around that nucleus orbits, say, a little particle called an electron. And this carries the negative part of the charge. It's this little electron that carries the negative charge that makes up electric currents in wires. Electron. It turns out this and this, these charges are opposite, and which belies a fundamental rule of electricity. Opposite charges attract, and like charges repel. Repel, that's right. And so the negative charge is being attracted to the positive charge and whirls around, around, around. In a very loose sense, in almost an incorrect sense. But we can think of it like a sun here and a planet going around and around and around. The force that holds a planet to the sun is the force of, we don't understand it very well. We have a name for it, begins with G. What is it? Gravity. And the force that holds the electron to the proton is the force we call, begins with an E, ends with an L. Electrical. It's the electrical force. So there's an electrical force between these two. Now we normally say that that atom has no net charge. You know what I mean when I say no net charge? There's as much positive as negative. In fact, if I had another charge, like a charge over here, a negative, this negative charge over here wouldn't even see that. It wouldn't sense it. It wouldn't sense it because this negative charge is what? Being attracted to the positive, but it's being repelled by the negative. And the distances are about the same. So it turns out it's a wash. So a charge over here doesn't notice electrically this atom over here. So the atom is neutral. So we have a neutral atom. But let's suppose this charge is closer, like over here. And let's suppose it's part of another atom, like another hydrogen atom. This charge here now is closer to the proton than it is to the electron. So there's an attraction to the proton, a repulsion over here, which is not quite as big, it's a little further away. So we have now a net attraction. And so you know what happens to this atom here? It clumps together and it becomes a molecule. When you study chemistry, you'll study about the different bonding forces. And all those bonding forces you study are, guess what? Begin with the E. Electrical. They're all electrical. You are held together by electrical forces. Electrical forces comprise all the bondings that you have in chemistry. It's simply electrical forces. And these forces behave in a way very similar to the way that gravitational forces behave. Remember we talked about the force of gravity? And we said the force of gravity, there was a force in the universe that was proportional to the mass of one object, the mass of another object, divided by the distance squared. Remember we talked about that? Well, physics is neat, gang, because guess what? It turns out there's a force that's very much the same between electrical charges. And that force depends upon the quantity of charge on one object, the quantity of charge on the other object, and depends on the distance squared. Isn't that neat? Whip, whip, same, same. Which is one of the nice things about physics. Things that seem so diverse really have a commonality. And so this is called Coulomb's law. Coulomb's, named after a man about 150 years ago by the name of James J. Law, right on, okay. And Newton's law of gravity is named after a dude named Gravity. Okay, we got it. Okay. But we have these two things here. And all Coulomb's law says is, hey, the force of attraction or repel, one difference. Electrical forces can attract or repel. So you can shield out electrical forces. Gravitational forces only attract. There's no way to shield them out. But you can shield electrical forces. But it just simply says the amount of attraction or repulsion depends upon how much charge you're talking about and how far away the charge is. If they're very, very far away, then the force would be very, very weak. If they're close, 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 the force would be strong. Just exactly what you would expect. The same thing you'd expect with planets in the universe, huh? Planets very, very massive, more force of gravity. Close together, more force of gravity. Same type thing with electrical forces. Any questions at this point?
Wouldn't a minus be part of the constant of proportionality for the electrical force?
I haven't even talked about constant of proportionality, but do you know what Lee is talking about when he talks about the constant of proportionality, gang? Remember the constant of proportionality for the force of gravity? If you took the force and divided it by this, you'd always get the same number. And that was that big G, 6.67 times 10 to the minus 11, okay? That was the constant of proportionality. Over here, if you take the force between a couple of charged particles and divide that force by the charges and the distance between, you'll get the same darn ratio no matter what setup you talk about. And that's the constant of proportionality, and we call it K. Over here we call the constant G. Now we don't talk about a proportion. We talk about an exact equation where G and K make this side and this side newtons, same. Other questions?
Yeah, if in the center of an atom you have more than one proton, which are two positive charged.
Yeah, this is for a hydrogen atom now.
Yes.
Let's suppose I had a helium atom. Now I've got two protons. Turns out there's two neutrons there too. And you know what's going to happen to the space over here? Take one guess. Everyone. This charge out here now sees two protons tugging on it. How many say it'll be pulled into a tighter orbit? How many say, no, it'll stay the same? How many say, no, it'll be pushed further away? Check your neighbor. How many say it's going to be tighter? Yay, that's right. And it turns out for a helium atom, the helium will hold the electron tighter. Furthermore, it will hold another one too. The fact that it holds another one makes it a little bit bigger, okay, because it's repelling over here. But a helium atom is smaller. And it turns out a helium atom won't gang up with any other atom. So there's no such thing as a helium molecule.
We have two positive charges right next to each other like that. How do you deal with that?
Why don't those two positive charges repel? Why don't they repel? Look how close they are. They're right up against one another. Why don't they repel? And let me say this. The electrical force is awesome. It's a billion times stronger than the gravitational forces between these particles. Billion. So there's an enormous electrical force tending to repel them. And why don't they simply repel? Well, it turns out you got to get to the last chapter in the book. And the last chapter in the book, you find out, honey, there's a force even stronger than the electrical force. Yes, there is, but only up close. And that force is called the strong force or weak force? Strong force, called a strong nuclear force. And there's a strong nuclear force that holds these things together in spite of the electrical repulsion. And later on, you're going to learn that when a nucleus gets too big, and these charges are far away, the nuclear force holding them together is weak compared to the electrical force, so they fly apart. And we'll learn that those atoms are called radioactive atoms. And all that has to do with the electrical forces between the nucleons. So there's another force that we haven't talked about that overwhelms the electrical. Any other questions at this point? Let's talk about charging. Here's a piece of cat's fur. It's for science. And here's a rubber rod. What I'm going to do is I'm going to rub the rubber rod against the cat's fur. Now what I'm doing... I don't know what that is. But anyway, what I'm doing here, gang, is what? I'm rubbing electrons from here onto here. And you know why? It turns out every substance is holding its electrons, yeah? How many say, oh, all substances must hold their electrons with just the same force? Coincidence of coincidences. No way. That's not true. Different things will hold electrons with more force than others. And guess what doesn't hold electrons very good? Begins with F, ends with R. Got a U in the middle. Try it. Fur. Or your hair. Okay. Guess what holds electrons very nicely? Begins with R, ends with ubber. Rubber. Okay? And so I take the rubber and I scrape it against the fur. What am I doing? I rub electrons from the fur onto the rod. Now, the rod has more electrons than before. You people in the front row, can you see those things? Hula, hooba, hooba. Follow me, I'll make your crops grow. Hey, boom, okay. It turns out, no, I'm kidding around, but there are more electrons on here than before. So I say this is charged. Now, you gotta tell me, negatively charged or positively charged? Neighbor. How many say negatively charged? All right. That's because the electrons themselves are negative. And by the way, do you know who was the one who gave us the idea of negative and positive charges? A first-rate scientist with a worldwide reputation in science. His name was B.F. Benjamin Franklin. That's right. Benjamin Franklin was noted as a first-rate scientist before he became a statesman for the 13 colonies. Benjamin Franklin did a lot of work in electricity. Benjamin Franklin is said to be the Isaac Newton of electricity. An enormously prominent scientist in his day, before the 13 colony type thing, and before signing the Declaration of Independence. Ben Franklin, he did a lot in electrostatics. So this then is negatively charged, and the cat's fur then would be positive, which, by the way, underlies a very important principle called the conservation of charge. And the conservation of charge simply says that, hey gang, whatever charge you got, that's what you got. You don't make any more, you don't make any less. All you do is transfer it from one place to another. It's like maybe a brick road. There's so many bricks in the road. Now I take some of the bricks off the road and put them on the sidewalk. What's the total number of bricks I have before and after? The same. I've just put them from one place to another. And every brick on the sidewalk is matched by a hole in the road. You see that? So we're just taking from one place and put another. So if I put a certain charge on here, let's say 1/1000th of a coulomb, coulomb is a unit of charge. If I put 1/1000th of a coulomb on here, and that's negative, what's the positive charge? 1/1000th of a coulomb, positive. You see that? It just kind of makes sense, okay? Let me get it's a ping pong ball painted with metallic paint. It's a conductor. Now what I'm going to do, the charge is wrought up. I'm going to put some charge on here, onto the ball. And I think you can see that when I get the ball charged up. Watch this now. Repulsion. Did you see that? So like charges do what? Repel. Now let's suppose I take this glass rod and I rub this against a piece of silk. Now this is going to become what? Positive or negative? How many say, oh, I don't know. It's going to be positive. And we can find out it's positive by doing what? Bring it over here and sure enough, you see that? Opposite charges attract. Okay. Isn't that neat? Here's a nice little thing here. Let's suppose I take this down and put a non-conductor up there. Like this piece of popcorn from packing material, huh? Let's try this. Okay. Now, that has no charge at all. Okay, if it does, it would ground off to me. I would ground the charge. But it's non-charged. Watch this. Even though it's non-charged, see that attraction? It attracted. Oh, it attracted, then repelled. Why is that true, gang? Oh, it's attraction, 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 and pretty soon I get enough charge on there, so... But you see, there's an initial attraction. Let me try that with a charge of opposite sign. Here's a positive charge. And it still attracts. Why? Why that's true is very interesting. It has to do with an idea called charge polarization. Let me show you what I mean. In this little piece of material here are little charges. There are just as many positives as negatives. When I bring the rod over, let's suppose the rod is negative. The negative does what? Pushes the negative part of those molecules over to one side and pulls the positive side, positive end, this way. For example, I have a little molecule like that. It will probably go like that, tend to point like this. Now the charge